Hello friends, welcome to this month webinar talk, Top 5 Java Performance Problems. And I'm Lakshmanan, I'm the architect of Ycrash. So let's get started with this topic. What are the top 5 Java performance problems? So in this session, what we're going to discuss is, we're going to see some of the commonly confronted Java performance problems and what are the efficient ways, non-intrusive approaches to troubleshoot that problem. And then I'm also going to be sharing with you the real world case studies with the real data that this problem happened in real major enterprises, how they went about resolving this problem. So that's what we're going to be discussing. Okay. And if you have any questions, feel free to put it in the chat or put it in the Q&A session. I will answer it towards the end of my talk. Okay. Thank you. Okay. So friends, the first major performance problem is external system slowdown. So this is a problem that we are seeing again and again and again. See, modern Java applications, it talks with multiple system of records, right? They talk with REST-based systems, database systems, mainframes, right now with AI applications, right? It's talking with various system of records. If those system of records slows down, or if there is any bottlenecks happens there, that cascades into our Java applications, and that is causing outages in our application. So we are seeing this pattern repeatedly again and again and again. So let's look into this, right? So here is an typical application architecture. Most of our Java applications conform to this architecture. See, we do have an application server. It could be a Tomcat, WebLogic, JBoss, Wildfly, right? And our application talks with various system of records in the backend. At the very forefront, there is a very precious resource called as a server thread pool, right? So here we have a thread pool. So whenever any new request comes to our application, right, when a new HTTP request, new customer request comes, a thread from this thread pool is going to pick up this request, and then it's going to make a backend call. And if the backend is going to give us back a response, once we get the response, we massage the response, we read the data, what is there in the response, and then we give back the response back to the customer request. Once the request goes, the thread goes back into the thread pool, right? So now let's envision a scenario. Let's say there is a slowdown is happening in the backend system of record. Let's say this backend system of record, typically it gives under a sub-second response time. Let's say for some reason, there's some hiccups going on and this application takes 30 seconds, 40 seconds, or 60 seconds to respond. Then let's see what's going to happen to our server thread pool, right? What's going to happen to the threads in the server thread pool. So let's say this is the system of record. It now started, earlier it was performing properly. Now it has started to slow down. Because it started to slow down, now let's see what's going to happen. Now let's say new HTTP request comes. The thread is going to pick up this request. It's going to make a call to the backend system. See, now the backend is slowing down. The backend system of record is slowing down. Now another request comes. So now a thread is going to pick up, a new thread is going to pick up this request. It's going to go make a call and it's going to get stuck because the backend is taking very long time to respond. Now another request comes, the thread picks up, we make a call, and this thread also gets stuck. So like this, when there is a prolonged slowdown is happening, if you don't have proper timeout settings, or even if our timeout settings are very large, right? All the threads are going to be getting stuck here. And now there are no more threads available in our server thread pool to service the new incoming request. See, this backend system of record, which is slowing down, it could be a very low volume system of record, right? It's a very low volume system of record. But even if it's a low volume system of record, because all the threads are getting stuck, the threads are drained, there are no more threads are available to service the new incoming request. So all the requests that are going to come to our application is going to start to time out. That could be one possibility if it is a low volume system of record. Or other possibility, let's say turns out to be a very critical system of record. This is a primary system of record. So a primary system of record is slowing down. And if you don't have proper settings, timeout settings, or thread pool settings, the threads are going to be stuck and the customers are not going to get response. So we are seeing this because we build a lot of dump analysis tool. When we look at several dumps, Number one reason why we are seeing outages is because of external system slowdowns, and we don't have proper timeout and proper mitigations, proper defensive code on our side to handle these kind of problems, right? So when this kind of problem happens, or not this kind of a problem happens, when any performance problem happens, how do we go about troubleshooting it? Friends, see, in production, no one is going to say like this, right? No one is going to say, oh, the system of record is slowing down. So take a look at it. What we get paged or what we get messaged is, oh, there is outage. Your application is becoming unresponsive. That's what we hear. So most of the performance problem, when we get reported, they are an unknown problem to us. The best way to attack any unknown problem is to equip ourselves with enough data. So here there is this open source script called as a YC data script. This script, you can trigger it like this. You can say YC minus P process ID, the Java process ID, which is slowing down. When you trigger it, this script is going to capture a 360-degree data from your application stack. It's going to capture all the data that we need to diagnose a performance problem. So it's going to capture a GC log, thread dump, heap substitute, network data, application log, kernel parameters. It's going to capture all the data, because the best way to handle any unknown situation is to equip yourself with enough data. So this script is a platform agnostic script. It can run on all flavors of Linux, Windows, Mac. When you trigger it, it's going to capture this 360-degree data, bundle them up as a one zip file, and then write it to your disk or in your container. Means you can specify a path where it needs to be written. So now we have this data. With this data, we can analyze and we can get to the root cause. Friends, when this kind of external system slowdown happens, and when that cascades as a problem to our application, the best artifact to use for troubleshooting is thread dump. Because thread dump indicates, so threads indicates, oh, they are getting stuck in the backend system of record. So best way to analyze these kind of problems is to analyze your thread dumps. So what is a thread dump? Thread dump is nothing but a photograph of all the threads that is running in your application. So it shows what are the threads running in the application, what is the code execution path. So how does a thread dump look? See, here is how a thread dump looks. You can see this is a typical thread dump. So here you can see at the very first, it's going to report what is the timestamp in which this thread dump was captured. And the next is it's going to report what type of JVM it is, whether 32-bit JVM or 64-bit JVM, what version it is. It gives that information. And our application tends to have hundreds of threads, right? So for each thread, this one segment is going to be printed. This one segment is going to be printed. Let's zoom into this segment and see what are the details which is there. If you see at the very first element, what it prints here is the thread name, the name of your thread. See, in Java, there's an API called set name in the thread class. So using that as a developer, I can give a name to my thread. So this, whatever the name I give using by invoking that API is, that's what's going to be showing up here. The next is a thread is going to can have a priority from 1 to 10. So 10 being the highest priority and 1 being the lowest priority. When there is any thread contentions, the thread with the highest priority get a chance to run first. Okay. And then the next one is, it prints the thread ID. That is, so this is the ID given by the JVM to your thread. JVM keeps track of all the threads. To keep track of all the threads, it needs an ID. So it assigns a unique ID to your thread. And NID stands for native ID. See, friends, thread is what? At the end of the day, thread is a kernel resource. It is an operating system resource. So kernel, in order to keep track of all the thread, it has its own identification mechanism. The ID it uses to keep track of threads is reported as this NID, right? But basically, this NID, thread ID, and name all points to the same thread, right? And then the next is, it shows the thread state. A thread can be in various states, like there is a 6 different states. We will see a little later. So runnable state means that the thread is executing on some lines of code. It's not stuck anywhere. It is executing some lines of code. And the 7th, probably the most important thing in your thread dump is the stack trace. This is the code execution path. So this tells you need to read the stack trace from the bottom. In Java, you have to read it from the bottom. Whereas in Python thread dumps, you do it other way around. But let's just keep it focused on Java. So here, the thread, this is the very first method the thread executed, the run method. From here, the thread went on to execute this method. From here, it went on to execute this method. So it progressed, and finally it is executing this method, itinerary segment processor set connecting flight. It's executing this line of code. So this is what it's telling. Friends, that's all the information which is there in the thread dump. But friends, with this information, we can do wonderful, wonderful things, because the threads are kind of the blood system of your body, right? See, think about it. In our body, if any of my organ is affected, let it be my heart, kidney, or pancreas, or anything, that it will be visible in your thread samples, right? The creatine level will be very high. The glucose level, if you're having diabetic, the glucose level is going to be high. So that's why doctors take thread samples to analyze what's going on. Similarly, the thread dumps are kind of the thread samples, are the kind of a blood samples. If you take that samples, you can see where the problem is going on. Let me show you how to analyze a thread dump, right? Friends, to analyze a thread dump, you can use these tools. These tools are available there in the market. You can use any of the tools that you want, or you can just open up in a text editor and also you can analyze. So for our discussion, we will use FastThread for analysis, right? So now, to do this analysis, I'm going to bring in a real world case study. So this is a real problem that happened in a major financial institution in North America. So this is a very major financial institution. Its products and services are used in 1 in 3 households, right? So what had happened was, since this was a middleware platform, the middleware, as we know, middleware platform talks with multiple system of records. So it started to slow down. If middleware slows down, none of the channels work, none of the lines of business will work. So the middleware's availability always has to be high. And it was starting to become unresponsive. At the time, this financial institution, they triggered that script which captures the 360-degree data, and they analyzed the thread dump. So let's look into the real thread dump. What has happened? Okay, so here is that actual report. So friends, you can open the thread dump in text editor and review, but it's going to be a little bit tedious. So what is this, this kind of fast thread, kind of a thread dump analysis tool does is, it has pre-built intelligence. It tries to recognize whenever there is if threads are all getting stuck. It looks for such patterns. It tries to look for such patterns whether that exists in a thread dump. If it exists, then it will raise it as a warning and report it to you. See, here, it's already here it's already reporting these many threads are stuck waiting for response from this Oracle DB. It can slow down the transaction, examine its stack trace. See how it is able to report this? Because it uses a pattern. Let me explain you that pattern so that even if you don't want to use a tool, still you can do a manual analysis. See, there is this pattern called all roads lead to Rome. See, there's a saying, all roads lead to Rome, right? See, similarly, whenever there is any bottleneck in your application, let's say there's a bottleneck in your application like this, that means all your threads will start to gravitate and go and they get stuck on this bottleneck. Like say, I may have like hundreds of threads. All the hundreds of threads, if there's a bottleneck, they're going to go and they're going to stuck on this one particular bottleneck. So what you want to do is, when you analyze a thread dump, you want to see whether at any particular method, there is a lot of threads are getting accumulated or not. You want to see if there's any method where a lot of threads are getting accumulated or not. See here, in this case, this application, you can see it has like 191 threads. It has like 191 threads. But in this 191 threads, here 87 threads are getting accumulated on this one particular method. Like there is kind of a 46% of the threads are getting accumulated on one single method. So now let's click on this to see, let's look at the stack trace. So if you see here, I'm looking at the stack trace. Here you can see this middleware was running on a WebLogic. And now you can see WebLogic, it is making a backend call. So it's going through this Oracle JDBC driver. It's going through this Oracle JDBC driver. And now it is getting stuck. It's not getting response because the Oracle database is slowing down. Like this so let me click on 87 threads are getting stuck. So let me click on some other thread and click on some other thread. So this thread is also coming through, but here it's coming through a different, there's multiple transactions, right, in our application. So in one of this coming through a different transaction, you can see it is coming through a lending code. The previous one was coming through some other code coming through. Finally, it is also going through this Oracle JDBC driver, and it is also getting stuck, waiting for response. So if you see multiple threads getting accumulated on one particular point, then that is an area of concern. This is going to be even more visible in the flame graph. See, this entire thread dump, the entire thread dump is a few hundred is a few megabyte file. So this flame graph tries to consolidate that few megabyte file into one single flame graph, and now it's bringing it to visibility. See how to read this flame graph. You can see there's like 174 threads are there in this application, right? They are all starting here. From here, 96 threads went on to execute this code path. 38 threads went on to execute this code path. So like this, they are all starting a different code path. But now finally, you can see finally it's going through this. Some of the threads are going through this Oracle code, and see what is the code. Finally, they're getting stuck. There are like 14 threads are getting stuck in this Sun IO file dispatcher IMPL read 0 method going through this Oracle driver. Now let me click on this one. Another tower, different tower. You see there are 9 threads. They are also getting stuck on the same method. Let me click here. Go to this tower. Here they kind of 6 threads. Finally, they are also going to the same method. Wherever they start, finally they are ending up in this file dispatcher until read 0 going through this Oracle driver, right? This problem is going to become even more visible if I reverse the flame graph. Let me reverse this flame graph. I can reverse the flame graph by clicking on this button, and I click. You can see now I click, the flame graph is reversed. Now we can see finally our application have multiple transactions, right? So they are like different towers. They are all different transactions. But finally, all of these transactions, you can see they are going through this Oracle driver, and they're coming and they're getting stuck here. So it is getting very clear and very obvious that the Oracle database is the primary system of record is kind of slowing down, which is kind of making this application to go unresponsive. So once they saw that now we are able to narrow down, yes, the problem is happening in Oracle rack cluster, then we can investigate what's going on and then we can fix it, right? Okay. So this is one of the very often confronted problem, that is the external system slowing down that cascades into our application. The best way to diagnose is take your 360-degree data and analyze the thread dump. It's going to give you the root cause. Okay. Friends, what I spoke, that is, look for a method where all the threads are getting accumulated. All roads load to read to roam pattern. That is just one of the patterns. Like this, there's multiple patterns that you can apply and analyze the thread dumps effectively. In the interest of time, I wouldn't be able to go to all the thread dump, but here is a YouTube video which you can watch on how to do thread dump analysis more effectively and efficiently. Okay. Okay. The second problem that what I want to bring up and discuss is the CPU spike. A lot of time our applications, the Java applications, suffer from CPU spike. The application may be going through fine, but all of a sudden CPU will go to 99%, 100%, and it will remain there. It will not come down, it will not settle down until you recycle. When these kind of problem happens, how do you go about troubleshooting it, right? Friends, even before going in there, let's see what causes the CPU to spike. What will cause the CPU to spike? So here is one example which is going to cause the CPU to spike. Let's say here I have a code, a Java code like this. While some condition, do something. Let's say I'm doing like this. Now, friends, think about what will happen if this condition starts to return true always. What if this condition starts to return true always? That means it effectively becomes while true. Then do something. That means the thread will start to go on an infinite loop. Thread will start to go on an infinite loop. Whenever any thread, see friends, whenever a CPU spike happens, it happens because of only one reason. The reason is the thread starts to go on some kind of infinite loop, or it continuously executes certain instructions, programming instructions in your application. But it's at bottom end is always caused because of threads. So you want to see if there's any threads in your application which is constantly looping or whether they're continuously executing some lines of code, then those are the threads which is causing the CPU to spike, right? So now, friends, I want to share with you one very, very effective trick. I like to use the word trick, right? See, our application. So, Fabrizio, you're having some question, just put it in the chat. I'll answer it at the end of the session. So, we all have used, there is a Linux tool, very effective tool called the top, right? The top command is there. Most of us would have used it. When you use the top command, we are going to see all the processes running on the device and what is the CPU and the memory consumption of each process of that device, right? We're going to see that information. But this top command has one secret option. Like this is that option. Top-h minus p process ID. This is a Java process ID when you give it as an input. This command is going to give us all the threads that are running within this particular process, within our Java process, and what is its CPU and memory consumption. So it's going to give me all the threads that is running within this particular process and what is the CPU and memory consumption. See, here you can see it's printing PID, even though it's printing PID, it's nothing but the thread IDs, all the thread IDs that is running within that Java process. Here it's going to say 31306, this is a thread, is consuming 69% CPU. There's another thread 31307 consuming 65% CPU. There's another thread 310308 which is consuming 64% CPU. These are the only 3 threads consuming CPU. All other threads are consuming only 0% CPU. So whenever a CPU spikes up in our Java application, let's trigger this command, top-h minus p process ID. When we trigger, we are going to see all the threads running within your process and what threads are consuming CPU. So now we have hundreds of threads. In these hundreds of threads, we are now narrowed down. These are the only 3 threads which is consuming CPU. All other threads are consuming only 0% CPU. So now I am able to narrow down. These are the 3 threads which is consuming CPU. Now my next step is to understand what lines of code these threads are executing. What are the lines of code that these threads are executing? So if I can narrow it down, then I can exactly pinpoint, oh, these are the lines of code which is causing the CPU to spike. So how will I know what lines of code these threads are executing? You can do it by capturing a thread dump, right? Because the thread dump shows what lines of code the thread is executing. So friends, this is where to troubleshoot this kind of CPU spike or any performance problem, this ycrash script comes handy. This yc data script comes handy. You can see this script, when it captures the 360-degree data, it captures 3 snapshots of thread dumps. It is configurable. Along with that, concurrently, it also captures this top-h output. That is whatever you're seeing, whatever you saw on the previous slide, it captures that. Now we have both the data. If we can marry these 2 data, because top-h is going to tell me what lines of what threads are consuming CPU spike, and thread dump is going to say what lines of code each thread is executing. When I marry these 2 data, I can get to the root cause of exact line of code which is causing the CPU to spike up, right? So this is a very effective and it's a very non-intrusive approach to troubleshoot the CPU spike. So now what we will do is let's look into a CPU spike that happened in a very major trading application. It's a very major trading application. It started to suffer from a CPU spike. So what had happened was this trading application, they would deploy. The application will run smoothly without any problem. But sometimes after a couple of hours, sometimes after 4 or 5 hours, sometimes just after a few minutes, sporadically, the CPU will spike up to 100%. Once it spikes to 100%, it will remain there until they recycle the JVM. Only after the recycling the JVM, the CPU is going to normalize. But then once they restart, either after a few minutes or few hours, once again the CPU will start to spike up. So this problem was going on. When they captured this 360-degree data, now we are going to look into the actual data. So now, when they uploaded, see here is that dump analysis. So when you upload your top-h output and as well as your thread dump to the fast thread tool, it marries those 2 data and presents you there's this section called CPU consumption at a thread level. This is very powerful, my friends, very powerful. And look at this script, this YC script is a non-intrusive thing. That is, it runs outside the JVM and captures your 360-degree data. It is non-intrusive. It doesn't have any noticeable overhead. So now it has captured the thread dump and married the data with top-h output. And now it is saying, oh, there is this thread called web container 18. It is consuming 60.9% of CPU. And there's another thread called web container 40. It is executing on these lines of code. It is consuming 26% CPU. Like this, it gives me a report. So now let's look into this report, this stack trace, this thread, which is consuming 60.9% of CPU. And I click here, you can see this application was running on IBM WebSphere server, right? It was running on IBM WebSphere server. You can see it is progressing, it is coming along. Finally, it is executing the weak hashmap.put code. Friends, look at this. This is the final line of code it is executing. Friends, hashmap is, if you look at the Java documentation, it's clearly said it's not a thread-safe implementation, right? If it's not a thread-safe implementation, it's not meant for thread safetiness. But what happens is, if you use this hashmap in a non-thread safe environment, that is, multiple threads starts to do a concurrent get and a put, they continuously start to do that, then the CPU will start, then the thread will start to loop infinitely within this put method. It will start to loop infinitely. So this is an age-old problem, which is there in the Java JDK kit. So thread will start to loop infinitely. When thread starts to loop infinitely, then CPU consumption is going to start to spike up. So whenever, since they were using a hash map by multiple threads in a non-thread safe environment, the CPU started to spike up. That's what was going on exactly here. The moment they saw this, they replaced this hash map with a thread safe implementation, which is a concurrent hash map. Once they replaced with a concurrent hash map, then the problem went away. But now look at this. The kind of CPU spikes and all can effectively narrow down. It clearly pinpoints, oh, these are the lines of code that is causing the CPU to spike. So you can get to the root cause fairly efficiently. Okay. So now let's move on to the third confronted problem. So that to the third confronted problem, which is out of memory error, right? So what causes a memory leak? What causes a memory leak? So friends, I have put together an hypothetical program which will simulate a memory leak. Let's look at that program quickly. Okay, so I'm starting my IDE. So here I have a program. So what is this program? So what causes out of memory error is? Say when you start to add objects into your memory and there is not sufficient memory has been allocated. So when there's not sufficient memory, and when it goes beyond your memory allocated level, then you're going to get out of memory error, right? So here is a hypothetical program. Let's look at that. So here is that program. Let me maximize my screen. So here is that memory leak demo, right? So it has an object one. This class has an object one, and the grow operation is invoked on that object. So now let me go here. In this object one has another child. It has a child object called as a map manager. And onto this map manager, insert records operation is invoked. So let's see what is happening in this insert records. So this is the actual method which is triggering the memory leak, right? So let's see what's going on in this insert record. Here it has an hash map called as a my map. It has an hash map. And now here it says, look what's going on. It says while true. That means if a thread enters here, it's just going to go on an infinite loop. So let's see what does it do within this loop. It says my map dot put key 0. I think my map dot put key 0. It's because the counter value is 0. And now it says the value it's going to put as large string 0. Large string 0. So it's going to say key 0, large string 0 is inserted into this hash map. And then for every 1000 iterations, it's just going to print I've inserted 1,000 records, 1,000 records, just going to print. So it just keeps on loop, and then it keeps on adding key 1, large string 1, key 2, large string 2. So just going to keep on build up the hash map with with lot of records. And when it go beyond your allocated XMX limit, whatever you allocated for this Java process, it's going to result in out of memory error. See, no developer is going to program like this. While truth, they're going to put like this. This is a hypothetical program, but this is how typical memory leak happen. They don't intentionally put, but accidentally they keep on adding records to a data structure. And if the data structure starts growing over a period of time and it goes beyond XMX limit, then it's going to result with out of memory error. So let me run this program. So now I'm running this program. You can see it is running. It is saying it is inserting 1,000 records, 1,000 records to, and now you can see after a point, it is unable to insert. See, initially and all it was inserting, but now it is not able to insert, right? You can see it is struggling. So once it struggled, then you see it confronted this Java lang out of memory error. So now it confronted the out of memory error. So this is how a typical out of memory error happens. When this kind of out of memory error happens, how do we troubleshoot it, right? Even I will talk about troubleshooting it, but friends, there is one effective technique which can, in fact, forecast the problem for you. Which can forecast the problem for you. Let me show you how to forecast, right? Yes. How do I even forecast out of memory error? You can forecast out of memory error by studying the garbage collection behavior of your application, right? Let me show. This is a garbage collection behavior of a very healthy application. Why do I say very healthy application? Look at this, my friends. There is request is coming, the memory is building up. Now, when the full garbage collection event ran, the memory dropped all the way to the bottom. There is a boom, there is a straight drop. Then once saying the request is coming, the memory is building up, and a full garbage collection event, the red triangle indicates a full garbage collection. When it ran, memory dropped all the way to the bottom. You see this kind of a beautiful sawtooth pattern, right? You see this beautiful sawtooth pattern. Now, let me try to draw a slope, a line connecting all the bottom points. If you see I'm drawing a slope connecting all the bottom points, you can see this slope is going at kind of a 0 degrees, right? It's going at a 0 degrees. Now, look at this garbage collection behavior of an application which is suffering from an acute memory leak. It is a slow memory leak. It's not aggressive, but it's a slow memory leak. Look what's going on. You can see the request is coming, the memory is building up, and a full garbage collection event ran, the memory dropped here. Right? It kind of dropped to kind of a 22 gig. Now, as time is progressing, when a full garbage collection event ran, it's dropping to 26 gig. Look, as time is progressing, when this event ran, it's dropping only kind of a 31 gig. If I try to draw a slope connecting all the bottom points, look at this, this is a black dotted arrow. It is going at a kind of a 8 degrees or a 10 degrees. It's not 0. It's going like this, right? If a slope goes like this, that means indicating this application is suffering from a slow memory leak. And once the memory leak becomes very aggressive, this is how the pattern you're going to look. You can see the memory is going up and down, up and down. Up. After a point, the memory is not coming down at all. Memory is now remaining here at the peak, right? At the ceiling limit. Friends, even when one red triangle, that is when one full garbage collection event runs, garbage collection consumes enormous amount of CPU cycles. It consumes a lot of CPU cycles. So even in one red triangle, if you see, your CPU will go up and then it will come down. But here you can see the red triangles, that is a full garbage collection is continuously running. If full garbage collection continuously run, your CPU is going to be at 99-100%. And friends, note down this point. Whenever there is a memory leak, your CPU will be at 100%. Whenever there is a memory leak, your CPU is going to be at 100%. So there's a strong indicator. Now you can look into your garbage collection log to see whether am I seeing this pattern. If you see this pattern, it's confirmed. Yes, you're having an outage. You're having a memory leak. But friends, look, all our monitoring tools, even Java's the out-of-memory error gets thrown only when we hit this ceiling limit, only when it is max limit. But if you can see several minutes ahead, the problem starts to happen. If you monitor your garbage collection activity, here itself you can detect, oh, it's the garbage collection activity is getting aggressive. If it gets aggressive, it means it's indicating you're heading for a memory problem. Right here itself, we can take your JVM out of the load balancer pool. Because when you take it out, you're going to minimize your customer impact. So if you monitor your garbage collection behavior, you can do such proactive measures. Okay. So now this is the way you can forecast the memory problems. But now, okay, so now the memory problem has happened. Out of memory has happened. How do you go about diagnosing it? So friends, diagnose it once again. You want to run this YC script. So this script, you can see it captures your heap dump as well. And then along with it also captures the GC log, two artifacts that we need to troubleshoot out of memory errors. So we have these two artifacts from garbage collection log, which is going to tell me the garbage collection behavior, so which can confirm the problem has happened. And a heap dump is nothing but a photograph of your memory. So it's getting a snapshot of your memory. So it's going to tell what are the objects which is there in memory, what values they contain, who are all referencing it. It gives me those kind of information. Those kind of information is needed to see what objects are leaking in memory. So now, once you have this heap dump, what are the tools that I can use for analyzing the heap dump? See, friends, you can use the tools like ycrash, heap hero, Eclipse Mat, or JAT kind of tools are available. You can use it. For now, for our discussion, we'll use this heap hero tool to analyze. So the heap hero tool, you can upload it online and then see. But now I have gotten the heap dump of this out of memory error, this program that what we discussed. I have captured this heap dump, and now let's look into that of how the heap hero reports it as a problem. So here is that heap dump analysis. So if the tool has detected any memory problems or any memory leaks, at the very top itself, it reports, okay, here there is this object. Map manager occupies 99.95% of memory. It is all the data is accumulated in this hash map. It's reporting that if you see here, this map manager is my class. This hash map is the one where the objects are accumulated. It tries to give it in a fairly simple English. It gives the exact class and where the accumulation is happening, it gives that information. If you want to see the details, see here is this, if you scroll down, there is a section called largest object section. Friends, whenever you are analyzing heap dump, let me show you how to do the heap dump analysis. Very easy way. Look at the largest object section. Always, memory leaking objects tend to be the top one or two or third object. If there's a memory leak is happening, that object starts to build up. So they tend to be the largest object in your JVM. Probably top three of them is going to tell you where the leak is happening. Because here it says, okay, here is this map manager. Thus, this object alone is occupying like a 99.95% of memory. Okay, then this is the leaking object. Now, my next step is I want to understand what is the content of this object. What does it contain? What is there for it to grow? To do that, click on this more icon and then click on this what's called as outgoing references. See, what is outgoing references? Reference means going outside from me. That is, what are my children whom I am referring to? That's what this outgoing reference is. So let me click here. When I click, here is this map manager. You can see this map manager contains the hash map, which tends to be the biggest object. If you see all other objects small or very small, few bytes, this is the biggest object here, which is hash map. Now let me expand it. If you see this hash map contains it has like a 1 million entries. It has like a 1,052,000 entries are there in this hash map. And these are all those entries. Now, if I click here, I can see the actual raw data. See the actual raw data which got created in the memory. You can see this key is 152,307. The value, the large string. 152,307. So this is what we were inserting in the code. You see the key value, I can see what is the actual raw value. Okay, so now I have this actual value known to me. So now I know, okay, this is the object which is growing and these are the content of it. But now my next step is, who is keeping this map manager alive in memory? Who is preventing it from garbage collection? So to do that, I want to see what are the incoming references. That is, who are referring this map manager to keep it alive. So I want to click on this incoming reference. So let me click on the incoming reference. When I click there, you can see this map manager is being referenced by this object one. Isn't it? If you remember our code, if you see this object one is what referencing this map manager. It shows this map manager is referenced by object one. It even shows me the variable with which is the reference, map manager. If you see, this is the variable name, map manager. And now if I want to see who's referencing this object one, I want to click here. Okay, I can see this object one is referenced by this memory leak demo object. So like this, I can walk through the hierarchy to see who is holding on to this object, keeping it alive in memory. All right. So in this way, we can get to the root cause of which object is causing the memory leak. So with this known, then we can go to the code and see what's going on, and then we can fix it. Okay. Okay. So now, my friends, I'm moving on to the fourth performance problem, which we confront in production environment. It is the garbage collection overhead. See, a lot of time when I speak in conferences or in some sessions, developers say, so garbage collection is automatic in Java. Why do we need to worry about it? What's there? It is automatic. Why do you need to worry about it? Right? It is true. It is automatic, but it can bite you if you have wrong settings. So let me share you a case study. But before even going to the case study, let me explain what is garbage. What does garbage means really? See, friends, all our application has a finite memory, right? So I can allocate my XMX as 10 GB, 50 GB, 100 GB, even half a terabyte, 1 terabyte, let you allocate. Still, it is a finite space. So let's say whenever a new request comes to our application, let's say a new sign-on request comes to our application, a new request came. This request is going to create a lot of objects in memory, right? Because when a sign-on request comes, if I'm going to use my Tomcat application server, the Tomcat application server creates its own set of objects. It's going to create a servlet to process this servlet, which we have configured. And then it's going to create HTTP request, HTTP response, HTTP session, HTTP filter. And now from there, I'm going to have my data access object, which is going to create a connection object. And then it's going to make a backend call. Now the database is going to give me back a result set, which is an object. So I create a lot of objects to service a simple vanilla request. So now I create all the requests. Now based on the database response, I may say, yes, the sign-on request is either the user is validated to start using the system or not validated. Now I give back the response to the request. Now the request goes. Friends, what happens to the objects we created now? These objects will tend to remain in memory, but there are no more reference to this object. Because the request has gone, these objects have now become orphan, or it has become garbage. It has to be removed from memory. Because only if you remove this garbage, the room is going to be available. There's going to be space in memory to process a new incoming request, right? Old unreferenced object has to be constantly removed from the memory. So these objects, which were very valuable, which served the request, once it has served, it is becoming garbage. How is this garbage removed from memory? Friends, 3-4 decades back, if you're a developer, it is your responsibility as a developer to deallocate these garbage from memory. I need to, so right now as a Java developer, I create only objects. I just say new customer object, new account object. I don't say free or deallocate these objects from memory. But back in those days, the developers were required to write code to deallocate the objects, right? But there are few challenges with that. Friends, you can see our business applications are very complex. It has multiple transactions, multiple workflows. Even if I miss to deallocate the objects in one particular scenario, in one particular workflow, then those objects will start to grow in memory. If those objects start to grow in memory, then we confront out-of-memory error. So out-of-memory error was pretty pervasive back in those days. In 1995, when Java came, it's 3 decades before when Java came, Java told to the development community, hello developers, you don't worry about deallocating or removing the objects from memory. As a runtime environment, it is my responsibility to remove the objects from memory. I will take care of doing it. Developers loved it because they can focus more on the business logic rather than doing this plumbing code. And management also loved it because it is less out-of-memory error. It was great. But friends, one thing is, even before Java, there were a few languages which was doing this automatic garbage collection. But Java really championed it. Since then, all the languages that is coming, they have this automatic garbage collection. Okay? Friends, this automatic garbage collection sounds good, right? It is good. It is good. But it has two side effects. What are those two side effects? The first side effect is, to do this garbage collection, it stops your application. It actually pauses your application so that garbage collector can see what are the active objects, what are the inactive objects, so that it can sweep them out. To do that, it momentarily pauses. It does not continuously pauses, but momentarily it pauses. So it does pause. So if your customer is saying, oh, your application was responding properly, but all of a sudden it didn't respond. But after that, it started to respond. If they say that kind of a statement, most likely the garbage collector was running in the background, right? So it pauses. This is the first side effect. The second side effect is the garbage collector consumes enormous amount of CPU cycles because it has to examine all the millions of objects which is there in memory. What are the references to that? What are the references to those references? So it has to walk through the entire object hierarchy. So it takes a lot of CPU cycles. So it has these two primary side effects. So now let's study this with a real world example, right? So how do I study the garbage collection behavior? How much time it is pausing? How much CPU it is consuming? What is the overhead it's adding to my application? Friend, the best way to study your garbage collection behavior is through GC log, because GC log is what contains all the minute details that we need, right? So you can study it through GC log. Once again, this YC script, Ycrash script captures you the GC log for you automatically. So now this is how a GC log looks. If you can open it in a text editor, you can look at it. It is a little bit cryptic, right? It has all these numbers. So you can use these kind of tools, like these kind of tools are available in the market. You're welcome to use whatever the tool of your preference. But for our discussion, we'll use this GCEC2, right? We will study this this garbage collection behavior. To study this garbage collection behavior, I got a real world case study from a very large cloud hosting provider. It is one of the top cloud hosting providers. Probably several of us are running our service on this cloud hosting provider. So what happened was, and this problem was happening in one of the critical service. One of the critical service was starting to slow down. It was slowing down. All through the day, it was slowing down. So they were studying the garbage collection behavior. Let's look at that garbage collection behavior of this cloud provider. So here is that garbage collection analysis report of this cloud provider, which was suffering from a poor response time. Friends, there is sections, the tool gives you a recommendation on how to improve the GC performance, all those things. But here, there is one section called key performance indicators. Friends, whenever you study garbage collection behavior, you want to look at what are the KPIs. The primary KPI, one of the primary KPI when it comes to garbage collection tuning is the throughput percentage. It says for this cloud provider, it says it is 96%. How does it sound to you? If someone says your GC throughput is 96%, how does it sound to you guys? For several of us, for most of us, it will sound good because 96% means it's a good number. If my high school daughter, if she gets 96%, it's a A grade. I'm extremely happy about it. But friends, this number, reporting it in percentage, is highly deceiving. Let me explain why it is highly deceiving. When someone says their throughput is 96 percentage, it means this application is spending 96 percentage of its time in processing the customer transaction and remaining 4 percentage of time in processing the garbage collection activity. So it means in 1 hour, in 1 day has 1440 minutes. Someone says 96 percentage throughput. It means 4 percentage of time is spent in garbage collection. That means what is it? It's kind of a 57.6 minutes per day is being spent in garbage collection. This application of a critical service of a cloud provider is spending 57.6 minutes per day in garbage collection. All these 57.6 minutes, it won't process your transactions. It's going to be just doing garbage collection. Let's go back to this report. Now, here there is this report which shows what is the pause times. How much time whenever an event ran, it paused. You can see, let me just zoom in this period. You can see at 11:52 a.m., a garbage collection event ran for 14 seconds. That means if any customer transactions comes during at 11:52, for next 14 seconds, it won't get response. And now, look at this. Another 7 minutes later, another garbage collection event is running and is stopping for 14 seconds. Like this, you can see continuously it is stopping. Since it's continuously stopping, they are seeing a very poor response time. So what they did was, they did a tuning exercise. So primarily, how to tune the GC performance. Friends, it is a little bit detailed topic. So here is a YouTube video I'm sharing with you for you to take a look at it. To see how we can tune the GC performance. There is actually there are a few tricks and tips I'm sharing here. If trying to take a look at it. But what they did in this case was, for this cloud provider, so they changed their young generation size. See, originally in this, when they were having the poor throughput, they kept the young generation size and old generation size as equal size, 14 GB, 14 GB. That's what they kept. Now, what they did, based on the GC tuning, they made their young generation size as 1 GB. Just one, they made very small. And the old generation size occupies the remainder space. When they did, look what happened to their throughput. It became like kind of a 99%. Phenomenal improvement. And look what has happened to the pause times. Look, their average pause time has become 138 milliseconds. Right? They were able to achieve this phenomenal improvement by doing this GC tuning exercise. Friends, when you tune GC tuning, your overall response time also gets better. Okay. So now I'm moving on to my fifth and the last problem, which is the concurrency issue. What causes the concurrency problems in Java application? It's because of lack of thread-safe programming causes this concurrency issue. So here's a hypothetical code, a Java code. I can declare any method as a synchronized method. When I declare a method as a synchronized method, what happens? When I declare a method as synchronized method, then that means only one thread is going to be allowed to enter into this get data method at any given time for that object. And only after the thread exits, other threads are going to be allowed to enter. Now let's discuss this hypothetical scenario. Let's say a thread 1 comes. JVM checks whether any thread is executing this get data method. No thread is executing. So it is going to be allowed to go. So now it has come inside. Now this thread, let's say it has gone to execute this do something method. But let's say this do something method takes very, very long time to complete. That means what's going to happen? Now, let's say another thread comes. That thread will not be allowed to go inside this method because the thread 1 is already working. Let's say another thread comes. It's also not going to be allowed to go because thread 1 is still working. Another thread comes, multiple threads comes, all of them, they're going to go and they're going to be stuck. They're not be progressed. Friends, what is a thread, my friend? Behind a thread, there is a customer is waiting because thread is what a customer request is being sent to a thread and thread is working. That means all these threads are not, if not allowed to go, that means the customer behind every thread is not going to get response. So it's going to slow down your overall application. When this kind of racing condition happens, the best artifact to use to troubleshoot is thread dump. So here I want to share quickly a case study of this racing condition, which disrupted the availability of a leisure travel service provider. Using this travel service provider, you make airline ticket reservations. So their service got disrupted. So let's look into that thread dump analysis report. So here is the thread dump analysis report. Whenever a thread gets blocked, it's not allowed to progress forward, where the tool paints you this kind of a transitive dependency graph. So it shows, okay, these are all the threads. All these threads are stuck by this thread. So this is a culprit thread which acquired the lock and it did not release, due to which all these threads are stuck or stranded. They're not able to move forward. So if you want to see what these threads are doing, I can just click here to see what they are doing. You can see the thread originated, was running on a Tomcat server. It was trying to invoke this random UUID. Friends, as Java developers, we use this API to generate random numbers. A lot of developers, we don't know that this is a synchronized method. That means only one thread is going to be allowed to enter this method at any given point in time. You see, it's trying to enter, but it's not allowed to go. It's put to the blocked state. Let me click on stack trace of some other thread. Some other thread also is doing the same, right? It's also trying to go to this random number. It's not allowed to go because it's put to the blocked state. So like this, you can see there are 646 threads are getting stuck. That means 646 customers are not getting response just from this JVM alone. And if you see, this is the thread which acquired the lock and it did not release it. Let me click and see what's going on. So if I click, I can see the stack trace. You can see this thread was also trying to go into this random UUID. It was allowed to go, it went in, but when it tried to generate the random number, it couldn't generate because of lack of, to generate random numbers, you need to have certain average algorithms installed on the kernel. The kernel was not patched with the correct algorithms to generate random numbers. So it was slowing down. So due to it, the entire random number generation was slowing down. So the application was getting into a grinding halt. So whenever this kind of concurrency problem happens, take a thread dump and then look at it. It's going to tell you where the problem is going on. Okay. Okay. So friends, I know we covered a lot of things very quickly, right? But if you want to do a little bit more deep dive, trying to understand more about JVM troubleshooting, how to analyze thread dumps, how to analyze heap dumps, how to do garbage collection analysis more in depth, here I have an online JVM masterclass. Here's a link for that. You can register here, you can enroll, and then you can use it, right? Friends, with this, I'm coming to the end of this month webinar series. We hold this series every month. You are welcome to attend and join, and we can have a discussion, okay?